making progress. But I would say I'm not there to unlock. That's why we have it 0, 1. So the fact that I'm making progress is indicated here, and that I'm going to another state. Okay? However, if I receive 1, and I know my sequence does not start with 1, it is not reasonable or logical for my machine to go to another state because it's not making progress yet, because it expects to see 0 first. So therefore, it sits there saying hint is 0 and unlock is 0. Why? Because I did not see the sequence, and I cannot feel happy because I'm not making progress. Okay? So that's why you have it there. Now, when I come to B, what did I see so far? I came to B because of here, so I call that half 0. I told you before, you can create or name the states the way you want as long as it makes sense to you. So here I have seen 0. Now, if I saw 0, and then x is 0, what's the value of hint in this case? 0, because I don't expect 0, so I'm not making progress. Hint should be a disappointment and say, no, you're not making progress. So therefore, what happens? You stay in that same state because you can consider the new 0 to be the half 0 that you have got. Or if you see 1, then you are saying, yes, I'm making progress, and therefore a hint is 1, and so on. And you carry on until you get both of them to equal to 1, 1, which means you have seen your sequence. You see, so just think about it at a very high level and put the states. And by the way, you can create many states. Don't worry about that. You can put many states because eventually you're going to be able to reduce them. But make sure that the states represent a good representation of the problem statement. Okay? So when we look here, when we talk about B01, B is a state, this is unlock, and this is the hint. Okay? If I give you this and I say design the circuit, you should be able to design it. If you get the state table, you should be able to design the circuit. I don't think you have a problem. Yes?
For design questions, will there be marks for efficiency?
No. In the design? No, I will not do that. The design, to me, simply apply the process to get the circuit. Unless I say, do this to get this, and that's a different story. But from a design point of view, it will be, get me a circuit that does the job. Yes?
Just for the state table, for the H state, in the last row, the H state,
yes.
When you get when you execute 1, then you should get a hint, execute 1. Then later on you get a 0, so I say you should have 9 states, 1 state after H. When you receive a 0, because according to your specification.
So here, when I am here at this state, that means I have received all of these. Is that right? So I can unlock now.
Yeah. All right.
You see? So now, if I get a 0, that means I go to B because I can say, okay, I unlock and I have a 0.
All right.
Yes.
I think he's talking about the question. The question says that if X...
You think he is?
Yeah, because
I think I answered this question.
Alright.
Just ask me a question.
Yeah, my question is, it says in the question that X is 0 and the preceding clock ticks are those. So we should expect X to be 0 again in order to unlock it. If you could pull up your question, original question.
Okay. Here?
Yeah, it says if and only X is 0 and the sequence preceding is that code.
That's right.
So we should expect one more X equal to 0 and then unlock it.
It's a good point, but very good point.
I read the question, so probably.
What's the connection? No, it's a good point.
Your mic died.
My mic died?
You just switch it.
Very good. Question here, okay? It's a very good question. The statement here says that if X is 0 and we have received the sequence, then we go.
Yeah.
Now, when we look at this one here, depends if you are implementing the circuit as a Moore or a Mealy machine. If you implement it as a Mealy machine, then this is right, because if you see 0, you go to B and produce that output, which is unlock. If you treat it as a Moore machine and you'd like to implement the x equal to 0 coming after the sequence, then you'll have to create another state, and that's what. Yes. That's why he's saying we need another state in that case. Is that right?
Yes.
Very good. Excellent. Any more questions? So these are the equations for the different states to design a machine like this. Now, one of you today in the morning asked me to deal with the issue of unused states. And the question was, if I have unused states, how can I make sure that the system will self-correct itself to come back to its sequence if for some reason it has jumped into an unused state? So this is what we are saying here. In general, not all of the possible combinations of the state variables will be assigned in states. Okay, so we can have some states that may not be used. So in power up, we might get the system to go to a state that's unused, and when it goes there, we don't know exactly what might happen. So it is very important to tackle this issue, and there are two possible scenarios. The simplest is to force, when you design the circuit, force all states to have some values. So don't consider them to be, don't care, give them some values, which means whenever you have an unused state, make sure that the next state in that, for that unused state, is a used state, okay? So, for instance, we determine that D is unused state. So instead of treating it as don't care, because if you treat it as don't care, you might consider that don't care values to be values that will lead to unused state. So what you do in this case, force your don't care values to be next states of used states, which means that you are forcing your circuit to always correct itself. So the simplest is to force all unused states unconditionally to go to valid states. Don't treat them as don't cares. A more efficient approach is to treat the values of the next state variables for the new states as don't cares, but in that case, the choice of the don't cares should force your machine to go to used states in case it ends up at an unused state. So the design must be inspected to ensure that these don't care assumptions don't cause the machine to stay, forever in a unused state. So the definition of a self-correcting machine is that if it happens to go to an unused state, the next clock will bring it back into the normal sequence. That's what you need to make sure about. Now, state reduction. Some of you expressed interest to know more about state reduction. So I'm going to go through some examples here and show you how, similar to what we did in the class, how we can do state reduction. So let us assume that we have a circuit like this. Don't, as this slide says, don't try to do state reduction by inspecting the state diagram. It's better to be more systematic about it. So as you can see, we put all the states, and what we need to do, we need to compare them with respect to, for a given state, where does it go, and what does it produce in terms of output. So you can see state C goes to A, F01, state E goes to A, F01. So clearly, both states do the same thing because they go to the same states and they produce the same output. So we can tell that these two states have to be combined. So you can do this for a small set of states and you will be fine. So you just have to compare them with respect to output and next states. But it's not that sophisticated if you have many states in your